Welcome, everybody. Thanks for joining my talk. First of all, actually, I wanted to mention how grateful I am to the organizers. In these difficult times, I think they pulled a really good job. So thanks for having me here in this very difficult times. My name is Fabio Tiriticco. My Twitter handle is TicoFab. It's a lot easier to pronounce than my family name. I come from Italy, but I'm based in Amsterdam. And I usually start by telling you who I am, but this time I would like to start by telling you who am I not, and that is an AI expert. So if you think about all this, marketing super cool hype images about AI, that's definitely not who I am. Who I rather am, I am definitely a Scala and Akka enthusiast and community manager based in Amsterdam, where I run the Reactive Amsterdam meetup. And also I am the organizer of one of the organizers of the Kubernetes Community Days conference, which sadly this year we decided to skip altogether because of this Corona situation. And so definitely not an AI expert, but I played with AI because I'm really intrigued by this topic. And so what I want to share with you today is a story of what I learned and what I achieved, and hopefully inspire you to go and learn and do some experiment yourself. So let's start with the use case, which is about planes. Now, this use case has a little story. This is a map of the surroundings of my office where I used to work when I started this project. And it's right next to the Amsterdam airport, Schiphol. Now, what you see in the map is that this part of the airport was the first one that was built. And then at a later stage, they had to build, because the airport grew and more traffic and all that, so they had to build another part, which is that one there. Now, what you see is in the middle between these two parts, there is that yellow highway called A4. So that was already there when they built the second strip. So the only solution in this case was to create a small bridge that connects these two parts of the airport. And the result, to me, it's really fascinating, is this small bridge that goes right over the highway with cars and trucks and all. And on this bridge, you see incredibly big planes. I've always been fascinated by this every time I drive under it. And then at some point, I was lucky enough to have an incredible view on this. So this is what I would see from the window. And I'm not sure if the picture gives you the idea, but it's really impressive to see all these giants move just on top, a few meters above cars. So I was fascinated by seeing all these planes passing on this bridge. And then I had this idea. I wanted to already experiment with AI. And so I had this idea, why can I grab a Raspberry Pi and take pictures of this bridge, and then I will train some sort of AI, in this case, you can see a deep network there, and then train this AI to detect whether there is a plane on the bridge or not. And if there is one, tweet it. So this is how it started. First thing first, setup of the Raspberry Pi. So there on the left, you see the Raspberry Pi at the window of my office. And then on the right, you see two images that it would take. So in the one on top, there is a plane on the bridge, and the one below, there is no plane on the bridge. This is the setting of our side project. And before we dive a little bit into how I implemented this, well, let's do a very quick overview about AI. So very quick what it is. Now, in fact, deep learning, what you see at the bottom, which involves neural networks, is a subset of machine learning, which is itself a subset of a general artificial intelligence. And machine learning in general is this idea of being able to predict some sort of result that the machine has not seen previously, based on what the machine has learned before. And deep learning is a subset of this group, where the distinctive feature is the use of neural network. And in general, all machine learning and deep learning projects, they fall into this goal of climbing the so-called pyramid of wisdom that maybe some of you have already seen. The idea of this pyramid is that at the beginning of a project, you start with raw data, which is raw collection from the real world. Then when you refine it, you format, you parse it, it becomes a refined piece of information, out of which we can try to extract patterns. And we start to create knowledge out of this information. And finally, we use these patterns, this knowledge, to create wisdom and make choices about our problem. And so typical applications of machine learning and AI, they sit at about those levels at the top. And two common uses of machine learning and artificial intelligence nowadays are these ones. The first one is regression, which is basically when a machine helps us answer the question, how much? So for instance, a linear regression, what you see there, might create a correlation between, say, the square meters of a house and the sale price and things like that. So the machine can identify a function that predicts well what the price will be. And the other use case is classification, which is basically answering the question, what kind? Now in this picture you see on the right is the famous case of training an AI to discriminate between chihuahuas and blueberry muffins. Actually, it's pretty difficult even for me with some muffins and some chihuahuas to do so. So in this case, the AI will have an output, a possible output of two classes. The image that you give it, it's either a chihuahua or a blueberry muffin. And in fact, this is exactly the same with our use case. We want to basically look at an image, and then if there is a plane on the bridge, that's one class, and if there is no plane, it's another class. All right, so now that we set this idea, we can think about how we are going to build our AI. And here, when I started learning about this, came a little bit my first revelation. And the revelation for me was that AI building really is still at the stage of trial and error. Especially in deep network. So I'm going to say from now on, when I talk about AI, it's about deep networks. We know that certain deep network architectures work better than others at solving certain problems, but that's all we know. There is not yet a sort of scientific, rigorous method to create a sort of an AI that we know for sure it will do its job. All we can do is try and apply these architectures, maybe tweak it a little bit, and build on the knowledge of those that came before us. Really, we are at a trial and error stage. Fortunately, there's a lot of work that has already been done there, and these architectures are well known. And a few examples are on the next slide. So on the left column, we see some type of deep network and some typical use cases for it. So for instance, unsupervised pre-trained networks are good for trying to reproduce existing models. So maybe sound or handwriting and things like that. Convolutional neural networks, which is what we are going to use for this project, are about image recognition. So faces, animals, street signs, anything. The third category you see there, recurrent neural networks, that is, to me, was really the most complicated that I tried and studied. It's about processing inputs that are related to inputs that came before them in time. So if you think about speech or translation, any sort of real world thing that happens in a sequential fashion, and that is what recurrent neural networks are good at. So probably behind Alexa or Google Home, there's probably going to be a very powerful recurrent neural networks. We're not going to look at this today, but we are going to focus on convolutional neural networks. And let's see then what are the basics of neural networks in general, and then we'll see a specification about convolutional neural networks that we're going to use. The very, very base unit is the artificial neuron, which is, roughly modeled on the human neuron, on the brain neurons, the neurons that are in the brain of humans or animals. And the artificial neuron is basically a function, a mathematical function called transfer function that receives a number of inputs, weight inputs. So W1 that you see on the left, W2, Wn, and there's a function that sort of combines them all. This function will emit an output called actually net input, so it's a little bit confusing. And then after that, there will be another function called activation function. And typically the activation function, it's only a threshold. It's a way to decide whether the global output that comes out of this neuron will be passed or not. So this is quite important. The activation function will receive the value from the transfer function, and it will decide whether it's worth to propagate this information or not. There are many different types of activation function. We're not going to go into this, but this is basically, in all its simplicity, the idea of an artificial neuron. And now you're going to tell me, oh, but maybe this is not like, it's not very, very complicated. It doesn't seem very, very useful. Well, the power of this thing, you will see it when it's combined. So in this next slide, we call it multi-layer neural network. This is what a real neural network looks like. As you can see, if you look at the image from left to right, there are many, many layers. And the name actually deep network comes from the fact that the layers in between, in the middle, they're called hidden. So we don't really see what's happening there. And the way where this basically works is that imagine that all those arrows that you see there, they have weights. And these weights, they come from the training that we have done on the network. So the end result is, let's say on the left, let's say our input values are A, B, and C. Then the input layer is the first layer. We'll just say, take these values and propagate them to all of the neurons that it's connected to. And then these functions that are inside the neurons will do their job. And maybe some neurons will only propagate the signal in this fashion. But and if you see, for instance, in the second hidden layer, some neurons don't propagate any signal further. And so when we look at the output layer is only receiving information from 2 neurons in the hidden layer number 2. And in this case, and let's say the output values of this will be 2 and 5. Now, if we try and change the input values on the left, and now it's T, P, and G, maybe because of the weights and these activation functions, the entire configuration of the information that gets propagated change, and the output values will be 7 and 1. So now you see that as the number of these neurons in the hidden layers grow, there are an incredible amount of possibilities and combinations. And this is basically the reason why these networks grow. To be very powerful, they need to have a very, very large amount of neurons in their middle layers. This is the basic of neural networks in general. Now, let's take a little bit of a deeper look at convolutional neural networks. Convolutional neural networks are extremely powerful, and it's actually, if you ask me, it's the main reason why the world is recognizing the power of AI. because of the results that we have been able to achieve with convolutional neural networks, which, you know, these results are scary sometimes, but for sure very, very powerful. So where does the power of convolutional neural network reside? Now, I bet as soon as you looked at the image on the right, you immediately recognized a cat and a rabbit, and you had no doubt which one was the rabbit and which one was the cat. But how would you teach this to a computer? If you think about the process that your brain has done to identify the cat and the rabbit, you probably haven't realized, you immediately knew. But if you try and break it down, maybe your brain must have gone through some steps like, oh, these two animals, they both have 4 legs and they both have black and white fur. They both have 2 ears, but maybe the ears of the rabbit are a bit longer, and maybe the eyes of the rabbit are on the side and the eyes of the cat are in the middle. And so if you decompose this, it's very hard for us to do it, but our brains have sort of gone through these steps, especially when we were learning, when we were kids, first learning to, you know, distinguish a cat from a rabbit. Now, the power of these convolutional neural networks is exactly here. They are able, given the right, a very big amount of images, to automatically understand what are the features that make a rabbit, and a cat. And they are able to identify these features and sort of see the whole part, the whole combination of this. So for instance, if we go in the next slide a little bit more in detail, the basic idea here is that a network that you train, in this case, let's say we're training a network to recognize rabbits. Of course, what I'm saying is an approximation, but the basic idea is that the network can learn some filters that apply to the training images. They see the features of the rabbit. So imagine that the grid that you see on the bottom left image is at a pixel level. And imagine that you train this network with thousands and thousands of rabbit images. Well, the network is able to learn the rabbitness of a rabbit. It's able to understand which filters needs to look at the image through to understand that there is a rabbit. We don't exactly know how the network does. It does so by changing all the weights on all the neurons in the hidden layers. Those weights somehow mysteriously, well, there are some techniques, but the end result is a bit mysterious. They get tweaked to be able to distinguish between a rabbit and other objects, for instance. This is a bit of a high-level overview of how they work. And a very typical convolutional neural network architecture is the one we're going to see in the next slide, this one here. If we read it from left to right, you recognize a little bit the layers we've seen before. So we'll have an input layer, and then there's twice a couple of layers, which is a convolutional layer and a subsampling layer. So the convolutional layer is the layer that sort of learns these filters about the image and the object that you want to recognize. And the subsampling layer basically sort of reduces the bandwidth. So takes this filter and sort of reduces them for efficiency. Then it's passed to another convolutional layer and another subsampling layer. And then finally, we have a dense layer of 500 neurons that are fully connected. And then all these 500 neurons will sort of collapse the result of their information into the output layer. And the output layer will tell us, for instance, at the end of this processing, whether there is, say, a rabbit or not. Now, something I didn't mention before is for all this to work, all the images that you train the neural network with, they need to be very precisely classified. So if we're training, I'm going back to one slide. If we're training a network to recognize rabbits, we need to give it thousands of rabbit images that we have classified, say in this image there is a rabbit, but also images where there are no rabbits, so the network understands the differences. So all this is a lot of work. And now, if we look at how I started to implement this, I have done, with Scala and DeepLearning4j, I have done exactly this kind of work. I have taken thousands and thousands of images of that bridge, and I've looked at all of them one at a time and classified them. So in order to reduce the complexity of the image, I cropped the images around the bridge where the planes would be and classified each image, whether there's a plane or not. And once you have created this data set with planes and no planes images classified, then you're ready to start the training. And what you want to do when you start the training is you want to split this data set in two parts, preferably random, where you take 80% of your data set and you use that set, the training set, to train the network, and the rest of the images you can use to test the network after you've trained it. So to check its performance, how well the network is able to behave, to recognize planes in images that it had never seen before. Well, once we're here, we are ready to start a little bit of coding. And here we really see we're going to use DeepLearning4j, this library, in action. And we will start with some settings. So for instance, my images that I'm going to train my network with are of those dimension 25 pixels height, 171 pixels in width. There's really no reason why this, I mean, probably there was a reason back then, but I don't remember, but they are just magic numbers. It could be anything. And then we have a depth of 3, which corresponds to the input channels, the RGB. So each pixel will have a different RGB value of red, green, and blue. The possible outcomes that we want when we feed such images to the network is it's 2 possible outcomes. So plane or no plane. And now in the next slide, we're going to see how this is the same image you've seen before about this architecture, how we can build it step by step using Scala and DeepLearning4j. A couple of premises before I start showing you these steps. I tried TensorFlow at the beginning to sort of compare, but for some reason I liked DeepLearning4j better. I'm not sure why, I couldn't say exactly why. Maybe because DeepLearning4j was built for the JVM, whereas TensorFlow, I don't know, the Java API, I didn't really like them very much, but this is not to say that this is not a judgment in any way. This is just a personal opinion. And then second thing, the code that you are going to see here is sort of pseudocode. So if you copy paste from the slides, it will not compile. I changed it to make it a bit simpler, but I have put everything on a GitHub repo. You can see the link after this. And that is a complete example that you can actually download and use. So back to our building the network. We start a builder, and this is a bit of a Java approach. There is a Scala port of DeepLearning for J, or at least some wrapper, but I use directly the Java one. And so we start the builder like that. And then the second step is adding our first layer. This layer sort of combines both the red input on the left and the first convolutional layer, the first blue bar. And what you see in this layer is that there's a few parameters that we haven't mentioned, such as the stride. It's not necessary to know what it is now, but basically, if you see in the constructor of the new convolutional layer dot builder, it takes two numbers, 5 and 5. That means that the network is going to analyze the image, taking a chunk, a square of 5 by 5 pixels at the time. And this image has a depth of 3. Remember the RGB values. And then the stride is basically how fast this square of 5 by 5 pixels is going to move on top of the image to analyze it. And then there's going to be 20 outputs for the next layer. Then we add a subsampling layer, the first one, that basically, again, just reduces the bandwidth for further processing, for efficiency. If you see that kernel size thing, that means that it will basically halve the information that we have. We're gonna put next with the next convolutional layer, same as the first one, except there's gonna be 50 output branches, let's say. And then another subsampling layer, same as the previous one. Now, we're going to add a dense layer, so-called. It's a layer with 500 neurons that are fully connected, each one with one another. And all the inputs from the previous subsampling layer will go to all the neurons, all 500 of them. And all 500 of them will also propagate, or maybe they will be connected to the output layer, which we are adding now. And this output layer has the task basically to receive the information from the deep layer, and sort of based on that information and sort of tell us on the outside to which class the image belongs. So whether there is a plane or not. The final step is to specify that this is a convolutional neural network, specifying the input height and width and the depth again. And then that's it. And then we build the entire network. And the result that you have here is this representation in deep learning for J of this neural network architecture. The next step will be to actually use it. So train it and evaluate our network. So that means we'll have to read all the images, split them in 2 data sets, like I said. And then also, when we start the training, we need to give it a condition where to stop. In this case, we're going to tell the network to stop after 6 minutes of training. It's a very, very early stopping, let's say. And so if you look at the code in my repository, you will see how these work together, but this is basically it. You create a termination condition, some additional configuration, and then you start this trainer, and you will be able to save the model, the best model that the trainer could produce. And why am I saying best model? Because in the next slide, we're going to see a screenshot of the actual training. I actually had planned to do a live demo with the Raspberry Pi, but given the situation, a screenshot is all you get. But it basically looks like this. You will see that at every epoch, which is basically means at every time, at every round of training, the network will take all the images and train them with a random set of starting values, for instance, random set of starting weights and neuron. And then for each network that in this case we see, for each epoch, which in this case we see it takes about a little less than 1 minute, for each round, we will have a score. And so every time that we train the network, if the score is higher than the previous highest score, we'll keep that configuration as the best one. And if you scroll and if you look until the end, at the end, when we reach the 6 minutes of run, we will have the best score, which in this case is about 0.96. Now, the criteria of this score, as in what does it mean 0.96? This is a detail that I'm not going to go over, but it's basically how accurate the network is. There's a way to test how accurate the network is on the test data set that you have done. And this is it. At the end of this process, you will have a saved model that you can reuse. And finally, I want to bring this all together and just show you one slide about the pipeline that I used for the whole thing. And there it is. You don't have to necessarily read all of the blocks, but this is to show one important thing that is good to have in mind. In AI projects, the real AI part is only a very small bit. In here, you see the 3 main flows that I had. So one is to detect planes. So coming from the Raspberry Pi, the pictures, you need to detect the new pictures, and then trim the picture, crop it, and then ask the network to detect a plane or not. There's a Twitter flow that like every hour I want to tweet a picture of a plane. So you need to pick one and tweet it and then move the image somewhere. There is a train and performance evaluation flow where you want to basically constantly monitor how your network is doing and possibly improve it. And the real AI parts are those highlighted in blue, but the rest, I tell you, is 95% of the work. It's a lot of I/O, and then each one of those blocks can go wrong, and you need to recover from failures. So the actual AI is, the AI part is really not a lot. I personally built this with Akka Streams. I'm a big fan of Akka and its ecosystem. But yeah, this is basically the operations that I had to do. Files, moving uploads, and really a lot of I/O process. Now we have everything in place. What are the results of this experiment? The result is that there is an actual Twitter account. It's called PlanesOnBridge that will, for a few months, has tweeted about once an hour a picture of a plane on the bridge. There were only 11 followers. Some of them were fake, and the other ones were my friends and family. Not the most popular account out there, but it was a lot of fun. I used the library from Daniela Sfregola, Twitter for S, to connect to Twitter. And these images are still there. Not really useful, but kind of a fun thing to do. And once we have all these images, earlier I mentioned that you want to also evaluate how your network is doing, and how to evaluate a neural network performance. That's another little chapter that I want to talk to you about. And we use the so-called, in the next slide, confusion matrix. Basically, every time that you give your network an input and you look at the output that the prediction that the network gives you, this prediction can fall into 4 categories. On the left column, it could be true positive, which in my case, there was a plane on the bridge and the model actually detected it. But below, it could be a false positive. Maybe the network thinks that there is a plane, but there wasn't any. On the right column, you could have a false negative, which means that there was a plane, but the model didn't see it. So the model thought that it was no plane, but there was actually one. And finally, at the bottom right, there is a true negative, which means that there was no plane and the model did its job and didn't see it. So I looked at the performance of my network over these few months where it was in action, and which by itself, measuring the performance is a lot of work, because you need to look at every image and see whether the network was right or wrong. And if I plot all the data that came out of it, this is what comes out. But in fact, this graph itself is not really useful. Just simply counting the true positive and negatives doesn't really give us a good idea. So on the next slide, we're going to see some very important measurements that are more useful instead. These ones. One is the precision, which is the blue line on the graph. And the precision tells us how well the model avoids false positives. The red line on the graph is called recall, and it tells us how well the model avoids false negatives. These values are between 0 and 1. And so in this concrete example, what does it mean? The precision is quite high. It's often at 1. So that means, for instance, that during that day, if the model thought that a plane was there, there was actually 1. So no false positives. But the red line is actually, it's very oscillating, and it's not very good, it's not very high. So that means that the model wasn't very good with false negatives. In other words, it means that a lot of times there were planes and the model was not able to see it. So these two criteria give us a very good indication of how the model is performing. And so when I went down and tried to investigate why the model misses so many planes, there were a few reasons why things go wrong. And in the next slide, we're going to see a few examples. Yeah, the weather was a massive source of trouble for my network. So you see there's a picture where it's very, very foggy, very difficult to see the network, the plane on the bridge. In the picture on the right, it's raining. So all those drops on the glass, they totally confused the network, maybe didn't recognize a plane. In the bottom left picture, there is actually a plane. If you squint your eyes, you can see it, but the sun is just in front of it. And so the lights sort of make all the colors look very, very dark. And then also in the bottom right picture, sometimes I wouldn't get the whole plane. Maybe sometimes I only get a little bit. And so the neural network is asked to identify a plane, maybe only looking at it at its tail. And so for us, again, for us human, it's so easy. Sometimes we never realize how easy it is for us to understand it. But for a network that only sees the tail of a plane, that becomes a challenge. And so it missed a lot of planes because of these reasons. Another reason that my network had the performance that it had is the famous AI bias. Because I am based in the Netherlands, and this is Schiphol, the airport of Amsterdam, KLM is the national air company, and so a lot of the planes that will pass on the bridge are blue. So my network became really good at spotting blue planes, because of course in the training set there is an overwhelming imbalance towards blue planes. So what I observed is like when there was a blue plane, the network was like, oh, sure, there's a plane right there, I see it. But then if you put like a white plane on the bridge, the network is not so sure anymore. And so this to me was really a good example. It made me totally realize how AI bias is everywhere, and it's very difficult to avoid it. You probably remember the tragic experiments of Google, this and Microsoft from a few years ago. And even with such a, silly sort of playful project like mine, AI bias really plays a role. So this is something that we as humanity, it's really important that we think about it. This was more or less the story of my little side projects. What are the next steps for you? I would say first you can find a fun use case and a data set. You can build your own if you want, or if you want to start with mine, you can look at that URL. Of course, the slides and URL and resources will be available. Then, of course, you want to maybe learn a few more details about AI and convolutional neural networks. What I've done here is really just scratching the surface. It's just a big overview of the principles, but there's a lot more to learn about it. And then give it a go. Code a neural network from scratch and train it. I can recommend this book, Deep Learning, A Practitioner's Approach, from O'Reilly, is from 2017, so not very, very recent, but the foundation is really good. And yeah, at the bottom you have the link to the framework and my resources. And that was it for me. Thank you for attending, and please stay safe during this time. I hope that we can avoid the same tragedy that happened in my home country in Italy. So again, thanks for attending. Please stay safe, stay inside, and play with neural networks. Thank you very much.